All right, that's good enough. Hello, everyone, and welcome to CSCI-UA.0490, Spring 2022 edition, Special Topics in Programming Languages. I'm Edward Yang. Normally, I am a software engineer at Meta. I work on PyTorch as my full-time job, but I also part-time teach this class at NYU. Those of you who have joined us via Twitch, welcome. This year, I'm trying something a little different. I'm making it possible to also view this lecture via live stream. So the way I've set things up is that I have a Zoom call, which my normal students are, and then I'm also streaming my voice and my slides to Twitch. So I'll be monitoring the chats from both places. They don't mix. So if you're a student, a normal NYU student in my class, don't be worried about speaking up. No one else can hear you. I'll re-summarize your question anonymously if necessary. And I love these are live lectures. You know, in this age of remote learning, I could have just recorded these lectures and had them, be videos you could watch on your own time. But part of the fun of doing a live lecture is that you can actually ask questions and make me go different routes as we're going along. And so I'm hoping that this can be a very interactive and fun session. So that's all for logistics, I think. So welcome. So I want to first talk about what this class is going to be about. So some folks would be like, hey, a programming languages class. Does that mean that I'm going to learn how to write in different programming languages? And the answer is, well, no, not really. It's true that the first half of this class, we're going to basically do a crash course introduction into Haskell, and I am going to teach you how to write Haskell if you don't know how to write it already. But the point of this course isn't really to learn a whole bunch of programming languages. And really, the reason I teach Haskell as part of this class is because Haskell is a really good vehicle for talking about many of the things we actually want to talk about. That is to say, languages as a conceptual universe. This word conceptual universe comes from Perlis, and the idea behind it is that normally when people talk about programming languages, we pay a lot of attention to how many parentheses do I have to write? Do I have to put curly braces here or somewhere else? What does it look like when I write a function? And that's a very superficial way of looking at programming languages. And what the purpose of this class is about is to look more in detail into the underlying concepts that are inside of these programming languages. So we're not just going to look at the sales pitch, like all the things you might read on Hacker News. We're going to look at the fundamental building blocks that build up these languages. And the hope is that once you learn, something in one language, you can apply it and use it in other situations. Like, hey, you've joined a new job and you need to learn about, some new programming language that you've never seen before. Well, hopefully you've got enough building blocks, enough core concepts from other languages you've worked with that you can quickly identify what it is that you need to learn that's new and what it is that you can just bring along with you for the ride in those situations. So that's sort of what we want to look at. There's a lot of ways to approach teaching programming languages in the undergrad computer science context. And I actually just want to point out that there are two ways I could have gone about doing this approach. So the first way is what I like to call the Cmu approach. And it's basically, you're going to start from nothing. In the beginning, there was nothing. And then, from first principles, you're going to start building up small, test languages that, embody bigger and bigger concepts, sort of these fundamental concepts, you add them in one by one. And in this way, you get to understand what is going on in the language in its purest concept. Hi, Zed. So the lectures here are being simulcast on Zoom and on Twitch. Twitch is going to save VODs. I've set it up to do that, so you can view them there. And also NYU's Zoom recording is also going to save. And I'll try to durably save these lectures to YouTube as well. So yeah, if you have to miss class sometime, you can come by and take a look at that point. About the so you build up these languages from the first principles, and at the end you have something that looks pretty fully featured. It's got a lot of the stuff you expect to see, and you've really understood how things are put together. And the point is, the reason I do this slide is because I just want to say we're not doing that approach from in this class. Instead, this class is going to be all about looking at real-world languages, well, insofar as much as Haskell can be considered a real-world language, and distill out these concepts from those languages. So it's a kind of different approach. I kind of like the approach of building languages from first principles. It's just not what this class is about. So, in case you were deceived on that, that's the concept here. Okay, so what are we talking about in this class? And so I've already talked a lot about, how we want to dig into the concepts behind programming languages. And there's two other things that I want to emphasize as part of this class. So one is critical thought. So basically, I've said some of these things already, but I want to weigh when you come away from this class, I want you to be able to draw comparisons and assess the properties of different programming languages that you might encounter. So, instead of having to work things out, step by step, instead, you can easily say, oh, well, this is this kind of language as opposed to that kind of language because you have the, tools to understand these different situations. And the last part, and one that's very relevant for those of you who are taking this class for credit, is that there will be a lot of implementation in the homeworks for this class. So the homeworks for this class are basically a series of labs, except for one, which is just a good old-fashioned, write some text and submit it, and we'll grade it by hand. And what we will be doing is we will be basically implementing miniature versions of many of the features that we are talking about in class. So for example, the first half of this course is going to be about Haskell, and the culmination, the final project that you write in Haskell in this class, will be actually building a full-on Hindley-Milner type checker for a simplified version of Haskell, Cmu Haskell. And that's going to use all of the ideas that we're going to look at from Haskell in the beginning, and it's also kind of cool because you now know how type checking in Haskell works. And similarly, when we move into the second half of the class, one of the things you will be building is a full-on JavaScript interpreter, once again for a subscript of JavaScript, but you will be able to take JavaScript programs and actually run them based on code that you've written in this situation. Something different that I'm also doing this year is I've actually published all of the labs in advance. So let me see. No, it's fine. I'll handle this later. So there will be a link in the class for folks at NYU on Brightspace. When I post assignments, they will just be links to the GitHub repository. And for those of you on Twitch, it's one of the links that are the web links for the channel. It's PL class public on my username EasyYang on GitHub. And all the homeworks are there. So if you feel like getting a head start and you know Haskell already, feel free to go wild. We'll be going through these as things go on. And the reason why I think implementing these features is really interesting is because, well, one is that, when you have features in a programming language, like if I'm a language designer and I want to decide to put something in, I have to make a call, right? Which is this feature worth complexifying my implementation of my compiler, the language semantics? I have to make this call and decide whether or not it is actually worth it or not. And the second point, and one that I take from my time as an undergrad, is plenty of times I'd be like, oh yeah, that makes sense. I know how to do that. And then I'd go to the lab and I'd be actually asked to implement the thing that I'd learned about in class. And I'm like, actually, I have no idea how this works. And the act of, sort of sweating it through the implementation really teaches you a lot. So that's like the other important part. One more thing, because I am still kind of like pitching this class to you, which is like, why should you care about programming languages concepts? Especially like, why should you care about learning Haskell in the first half of this class? Like, are you really going to write Haskell in industry? Well, you could. Like in Meta, we have several teams which write Haskell full time. But I want to give a different explanation for why it's useful to study language features in this context. So when I was in grad school, one of my PhD advisors, John Mitchell, related to me this story from his PhD, from his algorithms instruction back when he was an undergrad. And he's like, hey, recursion is a good idea, though inefficient. You can use the idea in Fortran by storing the stack in an array. And what's going on here? Well, what happened was in the 1970s, from when this algorithms instructor was giving this quote, there was actually no recursive functions in any programming languages. So you didn't this thing that like seems very simple, namely calling another function while you're inside of another function, worked in a completely different way. And it took a while before programming languages were like, hey, this is a good idea, and we should actually support this natively. And instead, like in Fortran, you had to simulate it by like manually modeling the stack. So the idea behind like looking at languages like Haskell and like looking at, sort of very advanced features that, you might not use normally. For example, in one of our classes, we will talk about continuations, is that these futuristic ideas may be useful problem-solving methods now and part of the languages you use in the future. So there's two parts to this, right? One is that just because your language doesn't have a feature doesn't mean you can't use it in some context. So you might be like, oh, I have to write C++, but I know a little bit about how X works, and actually I can do a simplified implementation of it on top of the language. If you are familiar with the idea behind design patterns, oftentimes design patterns are a way of working around lack of actual support for things. Now, this is 2022, and languages have caught up a lot. A decade ago, I could have said things like, well, for example, you might not have anonymous functions in your language, and so you might work around it by like having inner classes or by using the strategy pattern in an object-oriented language. These days, most languages have these features, but it's sort of also a really good impetus, because when you look at these features in the context they come from, it also helps you understand how these have been retrofitted onto like existing languages that you're likely to use in these situations. And so examples that I like to give about futuristic ideas that are really useful are, the two I mentioned so far, higher order functions and continuations, but also monads, which we will, have a lecture on while we're talking about Haskell. Memory models, also something very important when you're writing concurrent code. So there's all sorts of interesting stuff that, maybe you'll have available in your language, but even if you don't have it available, you can still make use of it in your context. Okay, so overall, the way that this class will be structured is so I took a page from Norman Ramsey, who is a really good educator, and he likes to organize programming languages concepts into three main categories. So the first category is say more with less. So the idea behind this is, traditionally people, for example, didn't really like writing Java. Why didn't they like writing Java? Well, you ask someone like, oh, it's because when I write Java, I have to write a lot of boilerplate. I have to write a lot of code to do simple things. And there are a cluster of language features like first-class functions, like type inference, like pattern matching, like continuations, which basically let you say complicated things in a very compact manner. And that's important, not just to save your hands from a lot of typing, but it can also make algorithms a lot clearer when you don't have to deal with a lot of unnecessary bookkeeping. Instead, the language lets you express what you want to say directly. So the Haskell portion of this class is going to be all about saying more with less. The second category is about reliability and reuse. And the idea here is, software is kind of interesting because we're all about, taking code that is pre-existing and basically, reuse it in lots of situations. And there are language features which help you, take advantage of this reuse and at the same time avoid shooting yourself in the foot. Like, who hasn't ever, used some code and then come back to it in a year or 2 years and realized it doesn't work anymore? And how do you make sure that sort of thing doesn't happen? There are also language features that help deal with that. And the last category I'm calling cross-cutting concerns. And what I mean by cross-cutting concerns are there are certain things that you have to do, like memory management, like how do you actually deal with, I need to allocate some memory for the data that I'm working with and then, free it at some later point in time. And also concurrency, the idea of running multiple things at the same time in your programming language. And these concerns are super invasive. What I mean by that is when you have a language and you want to, have it work concurrently, actually you need to modify everything in your language to actually, handle this sort of situation. And sometimes it is just too difficult to do. For example, in Python, there's this thing called the global interpreter lock. And what is that? Well, it basically says that at any given point in time when you're running Python code, there can only be one stream of Python execution going at any point in time. And that's because it was a lot simpler and a lot faster to implement Python in this way. And, come today, you still are forced to deal with this inside a language like Python. And if you look like a very forward-looking language like Rust, Rust, makes very different choices about how they do memory management, and they had to basically do an entirely new programming language to make this all work out. So so these are very important because they affect everything, and so they're also worth talking about when we talk about programming languages design. This is only of interest to NYU folks. So this class will have a bunch of labs, but it's also going to have a traditional paper and pencil midterm and final. The midterm is going to be March 9th, and the final will be whenever the NYU registrar schedules it. I checked last week and the official schedule wasn't out yet, but maybe it is out now. And the way I'm organizing the midterms and finals, because this is an online class, they are going to be take-home exams, and they will basically be a bunch of paper and pencil questions, talking about various things that happen in the class, and you're going to want to figure out how they go. And the red line basically is like, this is the first part of the class, and then there's the second part of the class between these two things. Okay, I'm going to pause right now and see if there are questions. You can shout them out or type it in chat. Either is fine. Twitch, feel also free to do any questions. Yeah, the final is not going to be cumulative, so it'll only be on the second half of the class. Although there might be references to things on the first part, but it is not a cumulative final. There's another question, which is, are all the homework going to be done in Haskell? And the answer is half of the homeworks will be in Haskell, and then the second half will be in JavaScript. So that's why in the course description, it says some familiarity with JavaScript is going to be useful. I will talk a little bit about JavaScript, but I am going to assume that you know how to write JavaScript, and the labs will involve writing JavaScript. There's another question, which is, will there be a capstone project? To be honest, I think this class would probably make more sense having capstone projects for students rather than a paper and pencil midterm and final. But it's still in the midterm and final format. So yeah, that's how things are. I haven't really thought about how I would go about grading or helping people decide how their capstones work. There's another question from the NYU class, which is, where are the VODs? And I'll post them. I'll post an announcement saying where you can get pre-recorded things later. You'll probably have some more questions after this slide. So let me tell you about this slide as well. So more logistics stuff. The breakdown for grades is 40% is going to be the homeworks. 25% is going to be the midterm, and 35% is going to be the final. As I mentioned, the midterm and final are take-home pencil and paper. The homeworks are a little unusual, which is that I always run this class to encourage collaboration. And so you actually do not have to do the homework by yourself. You can do the homework with a partner and jointly submit one solution for the two of you. So when you submit your homeworks, make sure you very clearly say, who the two people the homework is for. But yeah, talking over the concepts of this class with someone else, that's something that I really want to encourage. And so the format of this class is that you can submit in pairs. Obviously, I think you'll get more of the class if you attempt to do the homework by yourself before talking to your partner. But and you're also welcome to submit the homework solo if that's how you want to go about doing the class. But I do encourage and allow you to work with someone else when you're working on these homeworks. The other point is the late policy for this class. So the homeworks we do on Monday, right before class. Well, actually, I'll accept up to 5 p.m. So, you can keep working on it during class. And everyone will get 3 late days, no question asked, but you can only use 1 a week. So, if you need a little more time, then you can take a late day and then just submit the homework on Tuesday. No problem. I won't ask any questions. And you get 3 of those for the entire class. There are 11 homeworks, so you can do that 3 times. Any questions about this slide before I go on? Or I should say, what are the homeworks? Yes, all the homework will be due on Brightspace, so just upload your homeworks there. There will be like usually 1 file, sometimes up to 4 files that you're supposed to submit. I guess you can also just tarball up the entire directory and upload that. One more thing that's worth mentioning explicitly, which is that the homeworks are due on Monday, except on the 21st and the 28th, those weeks, because we have President's Day on the Monday, and I'm not going to make you submit a homework on Monday. And then we push it back to the normal schedule after spring break. And yeah, the course website is on Brightspace. And if you want to find a homework partner, for example, you can do that on Brightspace. There's a discussion forum, and that's where I'll be answering questions about anything you might have about the class that you want to ask outside of class. Okay, so that's it for logistics. So if there aren't any more questions about this, I'll go on to the main topic. Oh, yes, great question. When are my office hours? So I was figuring out when I was going to do them, which is why they're not on these slides. And I have finalized the office hours, and they are going to be on Thursday at 8:30 p.m. till 9:30 p.m. And I know sometimes this is not an convenient time for folks, so I'm always willing to hold extra office hours if people want. So just get in touch with me one way or another, and we can work it out. I was trying to strike a balance between having office hours later in the week so more people can try things out. Okay. I don't know why Zoom is telling me that the meeting will end in 10 minutes. So what I'm going to do is I'm going to kick everyone out of Zoom because we're in a nice spot, and then I'll reconvene. I'll wait 2 minutes or so, and then we'll keep going from there. There's one last question that I'll answer, which is, are there any tutors or TAs? And the answer is no. Actually, I wish we could have a tutor for this class, but we don't. So for extra stuff, please feel free to come to office hours. That's what they're here for. But no, we just have a grader on the class. Okay, kicking everyone out of Zoom right now, I guess. Twitch, you're going to have to sit tight while I get this set up. Okay. Hopefully this worked. Give a second for everyone to stream in, and I will also open the next set of slides. Does anyone have any more questions, miscellaneous chatter, things they want to say? Oh, if I want to look for chatter, I need to make sure I actually open the chat window. There we go. There's a question from Twitch, which is how did I make the slides? I made the slides on a tablet, and I used the program called Zernal, which is a note-taking app written by a math professor, interestingly enough. And I also have patched it a bunch to support some features that I want for note-taking. Okay. Looks like everyone's here. Looks like everyone can hear me. So let's get started with the next part. Okay, so for the second half of this class, I want to talk a bit about JavaScript because JavaScript, well, one is the language you're going to be writing your homeworks in, and two is it's a really interesting language, and it kind of can be thought of as this class in a microcosm. So let's get to it. Once again, why JavaScript? Well, it's also a really important language. So it's the language that all of your websites that you run in your browser run on. And the other thing is that JavaScript also gets a rap for being a kind of nasty, terrible language. And that's not entirely unfounded, especially early versions of JavaScript, but there's also a lot of good stuff that has gone in the language. So it's a really interesting language to be like, yeah, this is how things can go bad in PL design. And also, oh, here's how things can go really well in PL design. So it's a language of contrasts, and that makes it really interesting to talk about. If we talk about like what parts of the class we're going to be seeing with JavaScript, we're going to look at first class functions in it. We're going to look about continuations in it. We'll be studying various ways of doing objects, and that includes JavaScript prototypal inheritance. So, we'll be talking about JavaScript in that context. And we'll also talk a little bit about memory management and how JavaScript does those things. That'll also be relevant in this situation. And just to talk a little bit about what's coming up in next lecture, Haskell is going to be all about expressivity features, and we're also at the end of this course going to come back to Haskell and use it to talk about concurrency, because Haskell has a really interesting approach to concurrency that scales really well in a lot of situations. And we can't only do JavaScript and Haskell because there are a lot of important ideas, such as doing classes in a typed context, which I just can't do in JavaScript because JavaScript by default doesn't have types. So we're also going to look a little bit in depth at C++ and Java, two other very widely used languages, and they'll be used to talk about some of those concepts as well. Okay, so what are we going to talk about? So I'm just going to give a little bit of history lesson about JavaScript. There's a really good Hopl paper, HOPL paper, which I will link in the lecture notes after this lecture, which goes through the entirety of the history of JavaScript in way more detail than I can do in this session. But I just want to give a little bit of the most important bits. Then we'll talk a little bit of JavaScript in a nutshell, go over some of the major, what I think of as language features in JavaScript. We'll detour slightly into the Lambda Calculus because that's something we'll be talking about later in this course. And I also think is, one of the things to give you a little taste for, what's coming up in this class. And then we'll just go through a whirlwind tour of various things that we are going to talk about in the future in 490 and how they're relevant to JavaScript. And I have more than half an hour, so plenty of time to do all of this. Okay, so let's get started. So let's go back in time to May 1995. And your name is Brendan Eich, and you have been hired by Netscape. And Netscape, on their cell call, they're like, yo, Brendan, we've got this awesome project for you. And we're going to hire you, and you're going to come work on Scheme for the browser. For those of you who don't know what Scheme is a variant of Lisp. It's a programming language with a lot of parentheses, and basically, Brendan is, a big fan, and he's like, okay, cool, Netscape, I will come. And so he joins Netscape, shows up, and Netscape's like, okay, we really, really need a internet language for our browser. And Brendan's like, yeah, so we're going to do it in Scheme, right? Because that's what you told me we were going to do in your cell call. And Netscape's like, well, actually, we were talking to the folks over at Sun Microsystems, and they've got this cool new language called Java. And their marketing team convinced us that we're going to do a branding thing. So, it's got to look like Java, whatever it is you do. And Brendan's like, oh my God, what have I gotten myself into? They had some sort of marketing deal, so it had to look like Java. And Microsoft is looming over because, they've got Internet Explorer, and it's like, oh, the web is going to be, taking over everything. And so Brendan is like, okay, so I need to write a new programming language. I can't use Scheme, nor can I use any of the other languages like TCL or Perl or, all those things that were lying around because they don't look like Java, right? And the marketing team is like, it's got to look like Java. So why don't I just implement a little prototype language that kind of looks like Java, but has a bunch of things in it? And so he literally does this in 10 days. He demos it to all of Netscape. They're like, hooray, this is great. This is awesome. And yeah, that's JavaScript. Actually, it took another year for them to embed it in the browser. So it's prototype really fast and then spend the rest of the time dealing with the integration. So what happened? What did this language look like? And what constraints was Brendan operating under when he was trying to design this language in those 10 days? And in ICFP 2005, Brendan gave a very nice keynote sort of describing some of the design goals for JavaScript during this time. And I've stolen one of the slides from this presentation. So he had a few goals. So one was he wanted to make it easy to copy and paste snippets of code. So the idea being someone writes some cool piece of JavaScript and you're like, dude, that is so awesome. I want to use that piece of JavaScript, which, causes little sparkly stars to fall off my cursor. I want to use it on my website. So I'm just going to copy paste that piece of JavaScript code and put it over here. And one of the consequences of that was, he wanted the language to tolerate, so-called minor errors. So that's why, for example, in JavaScript, you can omit semicolons, and there's some complicated algorithm for deciding where the semicolons should be. Another design goal for JavaScript was that it needed to be able to handle what we call events. So what do I mean by events? Well, when you go on a web page and you click around, you are basically doing interactions with your web page. And when you say click on something, when you move your mouse, when you type on your keyboard, those are all events. And so the whole point of JavaScript is to be a browser language. And so it needed some way to actually basically say, hey, when you click your mouse, when you mouse over my link, when you type onto the keyboard, I want JavaScript to do something in the situation. And so this event handling was inspired by another system that was in creation during that time called HyperCard. And it was one of the sort of key things that JavaScript needed to do really well out of the box. So Brendan was like, okay, how am I going about doing this? And he was like, I'm going to, put two really important primitives in the language to get this going. The first is I'm going to have first-class functions for procedural abstraction. And I'm going to tell you what that means in a second. The second is I'm going to have objects everywhere, and I don't have time to implement a full-on inheritance-based class system. So I'm going to use prototypes because that seems to be easy. And I'll also explain what prototypes are very shortly. And besides that, well, he only had 10 days. So everything else, nope, not in the language. And in fact, a lot of the evolution of JavaScript over time with the various, new ECMAScript versions and also the standardizations of more web technologies have been all about adding things to the language after, this initial push. Okay, so what do I mean by first-class procedural functions? Well, clearly there's a concept of function which is very easy to understand, which is if I want to define a function, and most languages have this capability, I want to say, okay, here's my function, and then here are the parameters it takes, and then here's some body that says what to do when those parameters are there. So to make a function first class, that means that you're going to take this function and actually they're not just going to be, like these things that you can't talk about inside of your program. They're actually going to be values. They're going to be things that you can assign to variables, that you can pass around, that you can, use in the same way you would use a number or a string or an object for say. And so first class functions, the piece of syntax that I've written here, function x, return x plus 1, well, notice that I haven't actually given a name to this function. And so this is an anonymous function. And it only exists as a value, say if I want to pass it to something. And the second part, which I said was about objects, and the object system in JavaScript was based off of Smalltalk itself, but the way you can think about it is, objects are collections of various properties with values associated with them. And so at the very highest level, that's all an object is, but there's sort of more to it, which we'll also get to very shortly. So what do I mean by, so in the earlier slide, I said first class functions. So one of the things about first class functions is that you can define them anonymously, you can pass them around as values. And in fact, the other important thing about defining first class functions is they have to be full lexical closures. So what do I mean by this? Well, let's take a look at this example code. So in this example code, we have a function called curried add. Don't mind the curry in the name. It is a Haskell term that talks about what this thing is doing. And what is this function doing? Well, it takes a single argument, x, and it returns a new function. So remember that I said in JavaScript, functions are first class objects. So I'm allowed to return a function because, hey, it's just a value, just like a number or a string. And what does this function do? Well, this function takes itself another parameter, y, and it returns x plus y. So let's stop for a moment, think about what we think this function will do. So how do I actually run this? Well, I can first start off by taking this curried add function and executing the function with some argument that's going to be assigned to x. So I'll go ahead and do that. And so I have g equals curried add 2. What is g? Well, g, as we said, is a function because that's what curried add returns. So that means I can call it again. And so what happens when I call it with the argument 3? Well, I'll print out the value 5. And when I run g with the argument 5, I'll print out the value 7. So what's going on here? Well, what's going on here is that if we sort of step back for a moment and think about, what did I name this function? I named this function add. So there's some sort of addition going on. And you can kind of forget about all the details and be like, hey, here's a 2 and here's a 3. I add 2 and 3 together and I get 5. And I add 2 and 5 together, I get 7. And you'd be right. That's sort of, intuitively what this code is trying to do. And what actually is going on here is that when I define this inner function, this function y return x plus y, I closed over, and that's why it's called closure, this value of x, whatever the value of x was when I called curried add. So this inner function remembers what the value of x was at that time. And so that's why it remembers that x was 2. So when you say, oh, and what, by the way, y is 3, you get 5. It's because of this memory. And so we call these closures because they are not only functions, they also have data associated with them talking about what the things are. This is a very quick explanation. We will have an entirely full lecture about how lexical closures work later in this class. So as I said, this is just a taster for things that are coming soon in this class. There's a question in the chat. Does JavaScript close over the value or the reference of x? And the answer to this question is a little tricky, but basically JavaScript doesn't have references in the same sense a language like C++ has references. So we close over the value. Now, this is a little trickier if I didn't pass in like X and I passed in, say, an object where I might be able to mutate it in the future. And the answer is, well, I would mutate the original object that was passed in. But once again, we'll talk about that in more detail shortly. So full lexical closures are a very advanced language feature. Actually, I should stop. Are there other questions about this slide so far? Some pattern. So full lexical closures are a very, very advanced language feature. And so a like very fun function you can write in JavaScript is what we call the Y Combinator. No, that's not the startup incubator that goes by the same name. Their name comes from this function, which I've written down right here, which is actually a way to implement recursive functions without actually like relying on recursion in the inner programming language. So there's a bunch of code here that doesn't really matter. Don't try to understand it, or try to understand it, but like understand it after class. And what effectively it does is when I pass it a first order function, like when I pass it a function, in this case it's an implementation of factorial, it calls that function with the function itself that you are trying to define so that you can, for example, do a recursive call in the body of the function. So you can implement factorial in this way using the Y Combinator. Yeah, so you can do a lot of stuff with full lexical closures. One question you might have is, why did Brendan have to add first-class functions to JavaScript at the very beginning, right? Like this seems like kind of an advanced language feature, and you might wonder if you could have gotten away with not adding them to the language. And the answer is, well, it actually matters a lot. Remember that I said that in the browser, we're all about event handling, right? We're all about, what am I going to do when you press some piece of some button on the page or when you type. So how do you express what should happen next after one of these events happens? Well, you probably want some code to run in that situation. So you probably need some way of talking about functions when you set event handlers. And one important thing is that, if you don't have first-class functions that can close over values, if you want, for example, your function to change depending on some data that was in the context when you assign the event handler, well, that's kind of very difficult to simulate in a language that doesn't have first-class closures. So by actually letting the functions remember data, you can, for example, have a for loop and assign different event handlers in a single line of code without having to separately type them out one by one because you need a separate function body for each case. So take it from me, if you don't have first-class functions in a language, it's very difficult to work around them. For example, in Java, they didn't have lambdas for a very long time, and so there was this very complicated mechanism of anonymous inner classes that you could have used instead for these situations. That was very complicated, and you would have much rather been able to just pop out a function that said exactly what you wanted to do in that situation. And in fact, remember that I also said that Brendan didn't add anything else in the language. So in many programming languages that you might use, there are various ways of doing what we call information hiding. That is to say, saying, hey, I don't want this data to be visible by other people. And why might you want to do that? Well, one reason is because these are internal implementation details, and you don't want to be able to, you don't want people to touch them because you want to be able to change them in the future. And in fact, in JavaScript, in the early versions, there was no way of hiding information. And in fact, the only way to hide information was by, doing a closure in this way. And we'll talk a little bit about that when we talk about encapsulation and modularity. Now is also a good time to do a brief detour into the Lambda Calculus. So I said, first, lexical closures are very powerful, and they're so powerful that in fact, you can write a programming language that only has functions. And in fact, this language will be what we call Turing complete. That is to say, you can run any conceivable computation in this language, and it'll take a lot of work, but you can actually do it. And this language that only has functions is called the Lambda Calculus. So I'm gonna briefly detour into the Lambda Calculus. So what's in the Lambda Calculus? Well, in the Lambda Calculus, this is a sort of bastardized version of the Lambda Calculus where I've added arithmetic operators. The true Lambda Calculus doesn't have any, but what you have in the Lambda Calculus, you have expressions. So, you can talk about various things. You have the ability to call define functions. So in the Lambda Calculus, instead of writing function open paren x close paren, the Lambda Calculus, true to its name, you define a function by writing a lambda, that's the Greek letter, and then the name you want to bind, and then a dot, and then the body in question. And then actually applying things in the Lambda Calculus, it's the same old, you just take your function and you take your expression and you juxtapose them, you put them together, and that just means call one with the other. So to just look over this example, here we have a lambda expression that says given an x, return x plus y. And so if I apply this lambda expression to the value 3, I will get a new expression that says 3 plus y because I've substituted in the value of x with 3 in this situation. Or here's another example, lambda z, that says I'm a function. I take z as an argument. What do I return after I get that argument? I get x plus 2 times y plus z. So when I run this with an argument 5, I get x plus 2 times y plus 5. Any questions so far? So in the Lambda calculus, we're all about higher order functions. That is to say, functions that take other functions as arguments, because as I said, in the Lambda calculus, you only have functions. So, you don't have any other choice. So you can define very compactly functions that do various things. And so, for example, here is a function that, given a function f, returns the function f composed with itself. So what do I mean by that? Well, what I mean by that is that imagine that the function f is a function that, for example, takes a number and adds 1 to it. Composing that function with itself would be the effect of applying that function twice to some value. So I'd add 1 to it, and then I'd add 1 to it again. And so I can apply this function to this other function in the situation, and I can sort of step through how this might actually work. And in Lambda calculus, things are pretty simple because they're only functions. And the way I would go about evaluating something like this is I'd do something called substitution. So what do I mean by substitution? Well, let's take a close look. So we've got our two functions. We've got the lambda f, that is to say this higher order function that composes a function with itself. And we've got this adder function, the function that takes a y and adds 1 to it. So what do I do first? So first, I'm going to substitute all occurrences of f with lambda y, y plus 1. So I'm going to go ahead and do that right now. Just doing that again. So once again, I took the f and I just plopped in that function in those situations. So I've got, there were two f's before, and now I have two copies of lambda y, y plus 1. And then I'm going to keep going. So I'm going to take this x, and I'm going to run this function with x. So what am I saying? I've got this function that takes in a y as an argument, and then it returns y plus 1. So I'm going to substitute all occurrences of y with x, and that gives me x plus 1, because, well, there's a y, now it's an x, so it's x plus 1. And I'm going to go ahead and do that again. I'm going to take that x plus 1, substitute y with it, and hey, now I've got x plus 1 plus 1. So now you can see that applying the function with a function that adds 1 gives me a function that adds 1 twice, because that's what I said it would do. It applies a function 2 times. So this reasoning mechanism is a way you can figure out what higher order functions are supposed to do without actually having to run them on sample inputs. And it also turns out it's how you go about implementing a compiler that, say, wants to do optimizations. This same thing, substitution, is how it goes about doing it. And of course, I said that JavaScript has first-class lexical functions. It can do everything that Lambda Calculus can do. And so you can write it, albeit in a more wordy way, by just writing a ton of anonymous functions. Function f, which returns a function that takes an x as an argument, that returns f, apply to x. In recent versions of JavaScript, you can use arrow notation to write this more compactly, and it actually ends up looking a lot like JavaScript. Okay, so that's enough about first-class functions. What about objects? So in JavaScript, objects are maps of strings to values. So in fact, if you define a new object, say obj, and you use the array bracket syntax to set some value in the situation, in fact, you are setting the property of the function in question. By the way, this is very old school JavaScript. In modern style JavaScript, you would try not to use a object directly in this way. You would try to use, for example, a hash map. But early JavaScript didn't have a hash map or a dedicated dictionary type, so people would just use objects to do all this stuff. And if you serialize data using JSON, dictionaries are just represented as objects in JSON. And furthermore, we said that JavaScript doesn't have a lot of stuff. So what they're going to do is they're going to say, hey, so we've got these objects. We've got these objects that let us set properties on them by mapping a string to some value. So if I need a concept of a method in JavaScript, well, I've got first-class functions. So first-class functions mean I can use functions as if they're just normal values. And so, well, methods are, why don't we just have them be function-valued properties? So if I say, take my object and I assign frob to be this function, n that takes a number n and then adds it into the property. If I call frob6 on that function, well, it is actually going to go ahead and update the property in that case. So in JavaScript, there's no extra notion of methods. That's not entirely true, but we'll see why in a moment. We just reuse the first-class functions to actually get us the same concept where methods are just functions that are stored on the object in question. So we also wanted some way of doing inheritance for objects. And here, Brendan was very influenced by this language called Self, which did inheritance in an unusual way, aka prototypes. So how do I construct an object? Well, we just use a plain old function to construct an object. So I define a function called car, and it takes in 2 arguments, make and model. There's some magic variable named this, which we'll talk a little bit more shortly, which I assign properties to. This, if you're like doing a JavaScript tutorial, they'll just say, oh, this is just the object they're constructing when you define this function. And then you use the special keyword called new, which goes ahead and, when you say new car, well, you call this function, but what it does is it creates a new object and then assigns the properties on it. And so now you've got your car like this. So if you go to some JavaScript tutorial and you're like, hey, how do objects work in JavaScript? This is probably the code you would see in this situation. And so how do you do inheritance in JavaScript? Well, all functions have a prototype property. And what you can think of the prototype as doing is it sets some sort of defaults for the object in question. So in this function constructor, we don't have any property that says color, but if we set the prototype to have a value named color called black, then when I create a new car, say an old, well, this car is actually going to have a property that's color, and that color will be set to black. And of course, I can override the color on a per object instance after I do that. And this was pretty simple to implement, and you can basically do inheritance in this way by basically setting up chains of prototypes between the classes that you want to inherit from. In ECMAScript 6, there is an actual class keyword. It took a while to get there, but it's still useful to know how prototypes work because a lot of code still uses them, and they're also a very interesting and different way to think about inheritance, especially in dynamic languages. Questions so far? What are your questions so far? Yeah, go ahead. Yeah, so what you would do is you would define a new function called Ferrari, and then you would set Ferrari's prototype to be car. And that's how you would go about doing it. I want to, yeah. That's a little garbled, so I will defer in-depth explanation on that to a later point in time. Okay, next slide. Also, I got another notification from Zoom that it's going to close the meeting in another 10 minutes. So I'm not sure how I'm going to deal with that. We'll see what happens. Okay, so more about this. So what is this keyword that I was talking about? So intuitively, this points to the object which has the function as a method, right? So if you're not paying too close attention, or you're coming from a language like Java, you'd be like, hey, when I define a method on the function, and I want to refer to the object in question, I'm just going to like say this so that I can say, okay, I want to refer to X. And in fact, what happens in JavaScript is that this is a magic variable that gets bound when you invoke functions. So when I call o.f with a parentheses, then what happens is because I use this method syntax to call the function in question, that causes this to be bound in this situation. There was a question which is whether or not prototype inheritance is better than classical. That's also a difficult question to answer. One thing that I would say is that prototype inheritance is nice because, as I said, it doesn't require a lot of work to implement. There's not very many concepts associated with it. And that's why Brendan went for prototype inheritance. Now, if you're writing software in a large context with a lot of people, you'll probably want to use class inheritance because it's very widely understood and most people will know what's going on. And prototype, there are a lot of weird things you can do with prototypes. And most people don't get pretty unhappy when you do it in that way. And so having a more restrictive inheritance system makes sense in a lot of situations. So I just want to get into some of the weirdness in JavaScript. So here's an interesting program. What does this program do? Well, I've got a variable O, and it's got x set to 10 and a method f which returns the value of this.x. So I said that functions in JavaScript are first class, and that's true. And I also said that, just a sec. I also said that methods are just represented as functions, and that's true. And if a method is just a function and functions are first class, that means I should be able to extract the value of the function from the object and assign it to some variable. And if I do this here, g equals o.f, precisely that happens, and I now have a function called g, which is just by itself, but its body still refers to this. And in fact, if I call this function g, I will get undefined. It'll say, hey, well, there's no value for x. I don't know what this is. In fact, if I set x in the global context to be 20, then when I call g, I will in fact get 20 in this situation. That's pretty strange. And it gets worse and worse. So let's say that I didn't want this to happen, and I, wanted, to remember what the, original object the method was bound to. And what I might try to do in this situation is, well, hey, Edward said that we have lexical closures in JavaScript, and those closures remember the context they were executed in. So what if I write a nested function called g, which refers to this, right? And if this is a normal variable, then what I would expect to happen in this situation is g remembers what the value of this is, and so I'll still get the object that I had originally. But in fact, if you try doing this and then go ahead and call the function in the situation, not only will it not work, but you will also break the normal method invocations of f, and you will always be going into the x equals 20 situation. And why this happens is a very long and sordid story going into how JavaScript goes about implementing this. And in fact, this is so bad that newer versions of JavaScript have tried to fix this problem. So if you, for example, used arrow syntax, things would work differently in the situation. And once again, going back to this course as a whole, one of our goals in this class is to just sort of learn enough about how languages are put together so that we can understand why weird situations like this happen and understand, oh yeah, that makes sense, even though no, it doesn't really make sense. Because there's going to be a lot of situations like this in languages all over the place, not just JavaScript. I see a question. No, we will not ask this. So yeah, so my point is not to examine you on the, nuances and edge cases of the JavaScript language. So this is more of an aspirational question, which is that, we should be able to understand, things about the language, and in return, you will get to know how these things work. But I won't examine you on this sort of thing. So there's another question, which is, so this isn't a variable, it's some magical name. And yes, in fact, that is exactly what happens. So this is a concept that gets bound when you call a function. And so the route to understanding why this happens is to basically understand the rules for, when this gets bound in function invocations in this way. And yeah, there's a lot of tips about how to work around this problem otherwise. Okay, so I'm going to go through a whirlwind tour of the rest of the things we're going to talk about in 490. And hopefully I won't get kicked out, but if I do, I'll just start the Zoom meeting up again. It's not much. There's just a little bit of extra. And then the end will just be free talk for questions or anything you want to see. Okay, so what else do we have? Well, we have a lot of things, and let me just go through them. So JavaScript's got stack memory management. And what do I mean by that? Well, it's actually very, very simple and so obvious that, if you've been programming, you might be like, yeah, what's the big deal? This is obviously what should happen. So what do I mean by stack memory management? I just mean that when I call functions and those functions define local variables that differ from the variables in the context I called it from, something reasonable happens. And in this particular answer, I called f with x. X is 1, and then inside I call g with x, and then y is 3 inside this inner function, so I get 4, and then adding it to y here is 2, and I get 6. That's like how you would like run this code in your head. And fortunately for you, you get 6. And unfortunately, this didn't used to always be the case, and your language has to actually do some work to actually make this happen. And so when we talk about stacks, we'll talk about like how this actually gets implemented under the hood. We talked about closures, how you can return functions from functions. JavaScript also has exceptions. So for example, if you want to say, oh, an error happened, and then go to some later part of code that may be nowhere near where your exception was thrown, so you can handle the error in question, that's a feature JavaScript supports. And once again, that's a kind of complicated feature to implement, and we'll talk about it in some more detail when we talk about control flow and continuations. Continuations, what's that? Well, you may be more familiar with this as a concept from JavaScript called Callback Hell. What's Callback Hell? Callback Hell is when you have a callback handler, say on mouse done, and you say, okay, well, I want some function to run in this situation. And when you're responding to this function, you might need to trigger some other event. For example, you want to set a timeout, wait until some amount of milliseconds have passed to run some other function. And callback hell refers to like when you have to like nest functions and functions and functions to like actually, define all of the continuations that you want to do. And there's a, what is this? Well, these are continuations. They're telling you what to continue to do after some other thing has happened. And there'll be some interesting stuff we'll talk about how this is kind of nasty and how things... Zoom kicked me out. So let me go ahead and reboot Zoom. Hi, everyone. I'm muted. Oh, hang on. Hi, everyone. Need to share my screen again. Okay, just giving it 20 seconds and then I'll keep going. Okay. So I was talking about Callback Hell and how you have these marching function declarations in this situation. And when we talk about continuations, we'll talk about how what is going on, why are there all of these functions, and there's a good reason. We'll talk about how this relates to monads, which are a way to prevent having to do all this stuff. And we'll also talk about async, because most modern programming languages didn't add monads as a full-fledged feature. Instead, they added a more narrow feature that is very much like monads, but only for this particular case, for handling this sort of situation. We talked a little bit about objects, but there's all sorts of other topics that we want to talk about in objects. For example, in objects, there are like sort of 4 things that I would say characterize what an object is. And that's one, dynamic lookup. That is to say, when you call a method on an object, you don't necessarily know what will get called. It can vary depending on what object you have. Encapsulation, which just says that when you have an object, you can hide things from the external world. Inheritance, which is a way of extending the behavior of a class with more information in the situation. And finally, subtyping, which talks about when you can substitute one object for another in some situation. And it's clearer to talk about subtyping in a language that actually has static types. So we won't talk about subtyping in JavaScript. We'll talk about it in C++ and Java. We're going to talk about garbage collection in this class. There's actually a very funny story, which is in Netscape 2. There was actually no garbage collection in JavaScript, so it just leaked memory, and you only reclaimed it when you changed the page somewhere else. Netscape 3 added reference counting, and Netscape 4 and all modern browsers have some sort of garbage collector which collects garbage. And we'll talk about these different ways of doing memory management in those situations. JavaScript is single-threaded but cooperatively concurrent. I said concurrency is a major cross-cutting feature, and it shows here because if you think about like when you have a web page, there actually can be a lot of different things going on at the same time, right? Like you can have your mouse moving while some animation is playing in the background, and that all works. And even though there is concurrency in JavaScript, any given piece of JavaScript code, only one line of JavaScript is running at any given point in time. And that's a very interesting thing that we will talk about in more detail when we talk about concurrency. So that's it for our whirlwind tour of all the topics in 490. So just to recap, what are we going to do? We're going to talk about how to say more with less in a programming language and what features let you do that. We're going to talk about reliability and reuse. That means talking about in detail what objects are, how generics work, what modules are. And then finally, we'll talk about some cross-cutting concerns that affect, if you were writing a language from scratch, you would want to know what your answers to these problems were, because everything else in your language is going to depend on what you decide here. Okay, so that's it for the first lecture. There's 5 minutes left, so I just want to open it up to free talk. I see some chat messages, which I forgot to bring up. So let me just first go off and answer these things. So there's one question, which is stack memory management is the implementation of some particular style of scoping. That's a good question. And what I would say is yes. It's true that it's just one particular implementation of scoping, but in fact, what I would say is that most implementations are done in this way. Like if you look at any programming language, there'll be a stack. So it isn't just a implementation, it's the implementation in this situation. There's another question, which is, don't closures break stack memory management since a variable should be popped out of the stack, it stays in memory? And yes, you are exactly correct. And so that's why when you're in a language like C or C++, they don't have closures by default. And there's some funny business with making the stack live. And so when we do the talk about lexical closures and JavaScript, we will look at how you extend the stack model to actually work in this situation. And when you write your interpreter, you will deal with dealing with all of the stuff you need to actually make it work in that situation. Other questions? And I'm also looking at the Twitch chat, so if folks on Twitch have any questions, I'm also interested. All right. Well, I'm more than happy to let everyone out 4 minutes early. So thanks, everyone. Oh, there's a raised hand. Yes? Yeah, that's a great question. And in fact, a long time ago, I used to not give any lectures on ownership, but there is a lecture on ownership. So yes, we will be talking about ownership in this class. The question was, are we going to be talking about ownership? There's a question from Twitch, which is, does JavaScript have something similar to Python's global interpreter lock? That's a good question. The answer is, I don't know the answer to this off the top of my head, but I think the answer is no, because, well, it's kind of weird because JavaScript is heavily sandboxed. So remember, its context is all about running things in the web. And so in the web, you don't want one website to be able to reach in and grab the credentials from some other website. So the sandboxing means that you can run lots of JavaScript things, all together, and there's ways to talk in between them. The global interpreter lock is more of an artifact of the C Python implementation. And I think modern JavaScript engines know how to operate concurrently, although there are some caveats. Modern JavaScript implementations are very complicated. But there is some level of sharing across threads that's allowed. For example, web workers lets you define JavaScript threads that run in parallel, and WebAssembly, which is sort of built on top of existing JavaScript engines, that also has support for multiple threads. Any more questions? All right. I'll let everyone go. Thanks everyone for joining. See you all next time. Sure. Yes. Yeah. So the first homework due date. This is just logistics for NYU. So the first homework due date is. So the question is about the Haskell homework. The first homework is due on Monday. Yes, I understand that's a very tight deadline. So on Wednesday, I'll be basically doing enough Haskell so that you can make a good attempt on the homework. And on Monday, the plan is to basically walk through the homework and just talk about some of the things in it after you've taken a good attempt at solving it yourself. So yeah, I know it's very aggressive. You'll have enough tools to work on it after Wednesday, and hopefully that's good. Does that answer the question? Okay, cool. All right. Thanks everyone. See you all on Wednesday.